So we did the 200 feet elevation climb to the ridge, and we stopped. I was feeling fine, and took my pulse. It was 210. And my husband, well, my boyfriend at the time, was like, "Sit down, we got to rest." And I was like, my heart rate goes up to 180 when I run on the treadmill. I mean, this is not that bad, and I'm feeling fine. But during that morning, then I had developed diarrhea. And diarrhea out in the mountains without a porta potty is not any fun. So my husband said, "You've got altitude sickness. We're going to just cut our trip short and go on down." It was really weird because the nausea wasn't constant. We actually carried my backpack on a pole between the two of us. But just a slight rise, climbing up a rock to shortcut around a turn in the path, I'd be nauseated, which is that little bit of exertion. And so it can affect people when you acclimatize to it. There's changes in the diameter of your blood vessels. There's an increase in the number of red blood cells, all right, all of which help you to increase your oxygen transport. Here's another way of looking at it. So at 8,000 feet, your PO2 is still right around slightly above 90%. And you can saturate your hemoglobin, not 100%, but you can saturate it pretty well. At around 11,000 feet, your PO2 is going to drop with exercise. So you might start to get some altitude symptoms here. And then between 18,000 and 20,000 feet, your PO2 is significantly less. You're not getting completely saturated red blood cells. So at 8,000 feet, up above 8,000 feet, you can start to get symptoms of altitude. This guy that died was just barely above 8,000 feet. And he said they'd gone with the group, it wasn't just the two of them, and there had been no discussion or no, look out for these symptoms or anything like that. And so this website that had his story was trying to get an increase in the awareness of the possibility of those symptoms. So mild acute mountain sickness, headache, nausea, decreased appetite. You're fine to continue on the trip, but you shouldn't climb any higher. You should not sleep at a higher altitude. In fact, the best thing is to descend. If you're going to have an extended trip, is to descend, to sleep, and then make up that distance as you climb the next day. Moderate AMS, those symptoms above, plus difficulty, coordination, getting your clothes on, stumbling while you walk. Severe, difficulty thinking clearly, and that's one of the conundrums of this, is the people that you're telling them we need to go down. So hikers in the Himalayas, people that are climbing Mount Everest, they're being told, you have AMS, we need to move you to a lower altitude, and they're like, no, I'm fine. And they argue with you on that aspect of it. It's kind of like the nitrogen narcosis in a scuba diver. You're not thinking clearly. And remember that guy was coughing the day before he collapsed, and the guy that was hiking in Peru? That's signs of pulmonary edema, okay? And that's the HAPE aspect of it. So, tightness of the chest, dyspnea at rest. He had 2 of these, all right? And then, of course, the effects of lack of oxygen on the heart rate. So I guess I had a rapid heart rate, but then even at sea level exercising, I get a rapid heart rate. And then high altitude cerebral edema is the effect of excess fluid around the cells, not the lack of oxygen so much. It comes from the lack of oxygen, but it refers to the edema, so the increased pressure of increased extracellular fluid around these cells. So, again, the neuromuscular components of those symptoms. It's not really understood exactly why these occur. This next diagram here is kind of hard to follow, but what I wanted to show to you is that hypoxia itself causes cellular changes in capillary permeability. And this can happen with hemorrhage and circulatory shock. When tissues don't get enough oxygen, the capillaries become more permeable, and you give them more blood, and all that does, more fluid, maybe IVs, and all that does is just leak right out into the tissues. And so there's a point of no return in circulatory shock, where no matter how much fluid you get, it's not going to stay in the blood vessels. Okay? So a similar condition with hypoxia causes an increase in capillary permeability. There is a loss of those plasma proteins, such as albumin, that help to retain fluid in the blood vessels. So as those leak out into the tissues, more fluid is going to follow. And just very briefly then, that extra fluid around the cells in the brain, with the skull not allowing swelling to occur, leads to cerebral edema and increased intracranial pressure. And in the lungs, leads to fluid in the alveoli and even less oxygen available to the tissues because of the pulmonary edema. Okay, so now we're ready to look at carbon dioxide's transport. And this carbon dioxide is produced at the cells, and so that's why I have this titled internal respiration. Remember, for our 3 stages, pulmonary ventilation was the movement of air in and out of the lungs. External respiration was the gas exchange at the respiratory membrane, both oxygen moving into the blood and carbon dioxide leaving, but we focused on the oxygen moving in and its transport. And then internal respiration is the oxygen moving out of the blood and the carbon dioxide from the tissues moving in, but we're going to focus on carbon dioxide because that's where it's produced. Okay, so remember, oxygen was transported by 2 mechanisms. One dissolved in the plasma, and the predominant one bound to hemoglobin. Those 2 mechanisms also occur with carbon dioxide. So about 3 to 10% of carbon dioxide is dissolved in the plasma. And that is what is going to be our key CO2. Remember, it has to be in the gas form to create a gas pressure. So the carbon dioxide is carried in the second component, bound to hemoglobin, is not exerting a gas pressure, so it's not contributing to the PCO2. So this is what, again, is our carbamino hemoglobin. Okay, that's about 20 to 25%. So this is the effect that we talked about. Remember, we said carbon dioxide doesn't compete with oxygen, but carbon dioxide will bind to one of the hemoglobin chains, and that makes it more difficult for oxygen, because that's what we were talking about, the effect of oxygen. Now remember, that was the Bohr effect. So the Bohr effect for carbon dioxide meant that the more carbon dioxide that bound to hemoglobin, the less oxygen would be able to stay interacting with the iron. The Haldane effect is the reverse of that. It's the flip side of the coin. The less oxygen is on hemoglobin, the more carbon dioxide can bind to it. So it's essentially saying the same thing, but a reflection of that. So deoxygenation of blood increases the ability to carry carbon dioxide. Right? And the Bohr effect was carbon dioxide binding to hemoglobin decreases its ability to carry oxygen. So we're just saying it in a different form. So that is about, now we're talking anywhere from 20 to 35% of the hemoglobin is transported similar to oxygen, not to the iron, but to the hemoglobin. And then most of carbon dioxide is carried as carbonic acid. So this is 3 to 10, 15 to 25, and approximately 7%. So carbonic acid is something we're going to talk on Tuesday when we talk about the controlled respiration. But one molecule of water, either in the plasma or in the red blood cell, will bind with one molecule of carbon dioxide and will form a reversible, through a reversible reaction, will form carbonic acid. Some of that carbonic acid will then further dissociate to form a single hydrogen ion and a bicarbonate ion. Not all of them, okay? So when we say carbonic acid, we're talking about the H2CO3. So carbon dioxide diffuses out of the tissues. Some of it will bind directly to the hemoglobin. Most of it will interact with water and form carbonic acid. Okay. Now, in the red blood cell, that will happen in the blood as well. Okay, that will happen in the fluid of the blood. However, in the red blood cell, we have an enzyme known as carbonic anhydrase. And that speeds up the rate of this reaction. So more of it, exactly, it's a catalyst. And more of it occurs in the red blood cell than actually occurs in the plasma. Now there's another factor that's more important when we talk about buffering, when we get to the urinary system. And the bicarbonate ion that's produced leaves the red blood cell and is replaced by a chloride ion and is available